Namaskar and welcome back to the course on statistical mechanics of phases and phase transitions. We'll start with a quick recap of the previous lecture. In the last lecture, we had discussed phenomenological Landau theory, and we were inspired by experiments to postulate the existence of an emergent field. This can be a vector, tensor, whatnot. We worked with vectors, and the emergent field phi, we chose it so that it transforms correctly under the symmetry of the system, and this symmetry is also inferred from experiments. So we studied this model called as the ON vector Landau model, and in this model the emergent field is an n component vector which transforms under orthogonal n by n matrices. So that forms the ON group, and our fields transform under those symmetries. Then what we worked out was we worked out the critical properties of such model for any n and in any spatial dimension, and we were able to see that it produces certain critical exponents, and most importantly we noted that Landau theory can produce very rich and complex phase diagrams, and it can address many different experimental systems. Okay. So what we'll do today is we'll look at the Landau results again, and we will make a critique of the results, and we'll try to see how to repair it maybe, and we'll try to improve Landau theory and introduce fluctuations. And if you recall, we had discussed the physics of superconductors and the phase diagram of superconductors very briefly in the last lecture. And we noted that there was a phenomenon by which when you reduce temperature, the system went to the superconducting state, and that superconducting state was stable to some amount of current, but if you passed some extra current in the system, then it will actually kill superconductivity. So there is a critical current. So we did not explore that physics using Landau theory, but we should try to see whether by improving the theory we can address those questions as well. So this is what we'll do in this lecture. Okay, so let's start with a look at Landau theory once more. So we have this Landau function L of phi which satisfies the conditions of analyticity, symmetry constraints, namely L of phi must be invariant under symmetry transformations on phi, and some phenomenological information which we introduced by some coupling constants in the theory, and saying that when the coupling constants are in a certain regime, then we have a broken symmetry phase and things like that. So what we then did was we said that the partition function can be written as integral over all the possible values of this emergent field e to the minus v times this Landau function. This is what we said. And what we did though was we ignored the fluctuations of phi, and we just said that okay, the best possible value of L of phi, which is where the L of phi becomes minimum, satisfied by this equation dl by d phi equal to 0, is the state that we will be interested in. So that is the Landau theory. And for the ON vector model, we found that the system has a continuous phase transition with a important point, specific jump discontinuity. We have an order parameter exponent beta equal to half, and the ratio of these amplitudes is 0. Susceptibility exponent gamma equal to 1, and the ratio, the amplitude ratio of susceptibility is 2. The critical response exponent is delta is 3. So this is the results that we found, and one of the things that we immediately noticed is that there is no information about n showing up in this, in the sense that these are the critical exponents for ON for any n, whether it is n equal to 1, which is the Ising model, or n equal to 2, which is the U1 or O2 model. So this is a bit of puzzle. It's somewhat disconcerting that the thing does not depend on n, and more scarily, it does not depend on spatial dimension, right? The spatial dimension does not seem to enter this discussion at all. So this is something that we should be worried about. So let's look at some data. So what do we know about critical exponents from experiments and simulations? In fact, we saw this in the first lecture of the course itself. Let me just revisit some of those data again. So what I'm showing you here are the critical exponents of the Ising model known today from variety of sources. It can be experiment, in this case most of it is theory. So in d equal to 2, we can solve it exactly. We ourselves have solved it exactly in the course, although we haven't computed all these critical exponents, but we have extracted some of them at least. And what we know is that these are the exponents. So for example, beta is 1/8, it's not 1/2. And when you go to d equal to 3, you see that you are getting close to 1/2, closer I should say 1/2. And by variety of techniques, we can also solve the Ising model in d equal to 4, and we get exactly 1/2 there. So this is not bad, because in d equal to, in 4 dimensions, these are exactly the Landau exponents that we have. So it seems that in d equal to 4 we are doing well, but not in d equal to 3 and d equal to 2. Okay. So what is the message of this panel here? The message of this panel here is spatial dimension is playing a critical role. Sorry for the pun, I mean it's playing an important role in the critical phenomena. So, so this is a bit, it's very clear that we are missing something in Landau theory. In fact, the information about spatial dimension is not entering the Landau theory in any significant way. Okay, so we have settled the fact that spatial dimension is important, that we already knew that, but now we see the quantitative results, and it seems that very high dimensions we are doing like t equal to 4, Landau theory is doing pretty well. So this is the message. Now let's look at the effect of n, that is the symmetry. So these are some known exponents for different n's in 3 dimensions. I am fixing dimension here. And you can see that there is some sensitivity. They are not exactly equal, they are quite different. In fact, they are discernibly different. And you can see that alpha can be negative in some cases, positive when n equal to 1, and so on. So you can see that this is clearly dependent on n. Beta has some variation with respect to n, and in fact sort of increasing with n. So you can see that the symmetry has some role to play again, which Landau theory is missing out completely. Okay, so I have not introduced the exponents nu and eta yet, so we will do that later in later lectures. So whatever exponents we know, alpha, beta and gamma, are not matching with Landau theory, and they do depend on the symmetry, they do depend on spatial dimension. Okay. So symmetry n of ON has an effect on the critical exponents. Critical exponents become Landau-like in d equal to 4. So unfortunately we live in 3 dimensions. So well, that's not so good, but yeah, okay. So the thing that we are finding from Landau theory is that all second order phase transition, irrespective of symmetry or spatial dimension, seem to pick up the same critical exponents. So we started this course hunting for universality, and Landau is giving too much of universality in a sense, right? So this is a bit, well, it's not so, it's not nice that we have too much of universality. So we have to figure out how to fix this problem. So how do we fix Landau theory? Okay, so this is the question. So let's start by looking again at what we did. So just 2 slides back, I showed you that we ignore all fluctuations, right? So have we seen a context in which we have ignored fluctuations in the past? And the answer is yes. We ignored the correlations between fluctuations in mean field theory, which is a microscopic theory, mind you. So what Landau theory is doing, you can now imagine, and by the way, you must also remember that Landau theory also produces exactly the same critical exponents as the mean field theory, which is a microscopic theory. So what we are now able to see is that Landau theory is effectively a phenomenological way of doing the mean field theory without going to the microscopics. So that is what is coming out of our analysis. The microscopic mean field theory and Landau theory are giving the same critical exponents. So that is the connection. So this statement here, Landau theory is effectively the phenomenological mean field theory. So we know that mean field theory is missing out on fluctuations. So we have to somehow weave in fluctuations into our story. So now when we look at this phi can have different types of fluctuations. Phi can have thermal fluctuations. That means as a, it can have different values of phi are have different probabilities, so they will have thermal fluctuations. And phi can also have spatial fluctuations. We have not talked about spatial fluctuations before, so it's worth looking at some Monte Carlo simulation data. Okay, so this is results of some program that I wrote some time back, and what I'm looking at is somewhere very close to TC. I am looking at snapshots of Monte Carlo simulations. So I just plot out in some, after the system has equilibrated, in some snapshot and at some time step, I just plot out the spins, right? All the red regions are up spins and all the black regions are down spins. So you can see that here there is a lot of variation. So this is like hundreds of lattice sites. So you can see that there is a lot of variations of spin very close to TC. So so here it looks like, if I look at around what is the magnetization in this region, I see that it is something like, it looks something like all up. Whereas if I look here, it looks all down. And if I look somewhere here, there are little islands of up in the down sea and things like that, right? And same thing here, there's all this patchy stuff. And if you look in this picture, you will see that it's primarily black, a lot of black and very little red, or some little red. And here you can see that it's completely flipped. So you see that it's mostly red and a little bit of black. So this is what I mean by thermal fluctuations, and spatial fluctuations are these things that are happening in space. So the system is not only fluctuating, it's picking up different configurations that have thermal fluctuations determined by the probability of associated with the energetics of that field. It is also undergoing the fluctuations have also some spatial character as is shown here. So somehow we have to include both of these things if we want to get closer to describing the actual phenomena that's going on, right? So this is why the Monte Carlo simulations actually are extremely useful. You can understand things. I hope you have written your Monte Carlo code and you have perhaps already seen these things in your simulations as well. Okay, so this kind of fluctuation physics is completely missed out in the Landau theory. The question is, how can we put this in? How can we improve Landau theory to put this kind of spatio-thermal fluctuations? Okay, so how do we treat these spatio-thermal fluctuations? Okay, so the first thing we have to do is, we have already seen from Monte Carlo etc. that we have to make our emergent field not some constant field like, not some constant number like phi. We have to somehow make it position dependent. So imagine that I have some periodic box of volume V, which is L to the power D. We are in D spatial dimensions, and periodic box of volume L to the D, and we are working in a continuum, right? So we have underlying lattice, but we don't care about it in the phenomenological theory. So what we are going to do is, we are going to first make this emergent field a space dependent function. So I'm going to say this is some ON vector field, if you like, right? So this is like a field, right? So how can you imagine this coming from microscopic picture? So I'll try to show you how to think about this field coming from a microscopic picture. It's something like this. So you have, so I'm just drawing you some spin configuration here with ups and downs and etc. And what I'm going to do is, I'm going to introduce an idea called as coarse graining, right? So I'm going to take up this lattice and I'm going to define some scale here, which I'm going to call as LC. So that is some kind of coarse graining length scale. So I'm saying here I've picked 3 by 3. So this is like 9 spins I'm going to keep in one cell, if you wish. So I'm going to take this big object here, the big sample or my system, and I'm going to sort of dice it up. I'm going to cut it up into little cells. Okay. And if I have a microscopic model, I could imagine saying that if you give me a microscopic spin configuration Si, I will define for you this variable, this emergent field variable phi of x as the average of all the spins within that cell, right? So this is the idea. So you are sort of, we will introduce phi of x phenomenologically later, but right now, suppose you are thinking about it from a microscopic perspective, which is what, for example, we are doing in the Monte Carlo. Given a Monte Carlo snapshot, how can I find what is phi of x? That is what I am trying to address here. So for example, I can, from each of these snapshots, I could use the trick that I had and I could compute a phi of x. Right? So that's one way to think about it. So what does this, it teaches, right? So it teaches us that, so to allow for fluctuations of the field, we have to make phi position dependent, and there is a way to understand what that phi of x means from a microscopic picture given a microscopic configuration in this fashion that I am showing here by coarse graining over some kind of cells. Okay. So this is the idea. Now I have shown this for the Ising model where this will become just a number, but you can imagine that this can be easily generalized to ON spins. So instead of Ising spins, you can think that there are some ON spins there and you can average this over the ON spins. And therefore I can think of the emergent field in this fashion. Okay. All right. So the phenomenological approach now is not to think about it from a microscopic perspective, but to just posit that there is a field phi of x which is some emergent field defined on a continuum arena. We don't even care about the lattice anymore, right? But the most important thing phenomenologically we know, because we have also been sensitized from the microscopics, is that this coordinate x that we have, it must not be measured with arbitrarily small least count, right? The coordinate x, for example, if I look at this, if there is LC here, the x can be thought of as the center of the cell. So I should not think of x somewhere in between now. The next x is somewhere here, which is LC away. So in some sense, there is a coarse graining length scale, which is an ultraviolet. Ultraviolet means short distance length scale. So this field phi of x should not vary on scales smaller than LC. So this is the idea, right? The key point is that the physics on the length scale smaller than LC is unknown to us. We do not know what is happening on scales smaller than LC. That's the phenomenological approach. You say that, okay, I think that I know I'm probing this, the smallest scale I'm probing is some micron something, and therefore I don't know any physics below the LC length scale. So so I'm just going to say that that is the smallest distance in my problem, if you like. Okay. So I have this phenomenological approach now. So there is a emergent field phi of x, and how does this field transform under the ON symmetry? Well, if you give me a field phi of x, I will just rotate. I'll just go to a point. I'll find the vector the phi of x there, and simply rotate it by the rotation matrix, and I'll get now a new vector field, which is everyone rotated by the same fashion, right? So this will give me the transformed field, if you like. Okay. All right. Now you have to ask see, this is the math of this is the statement of the physical desideratum, physical goal that we want to achieve. We have an emergent field. It must be sensitive of the fact that there is some small length scale below which we don't know what the physics is, and it must be able to transform correctly under the symmetry. These are the two things that we have done here. Now, how do we impose mathematically this ultraviolet cutoff scale? Ultraviolet means small distance physics is what we call ultraviolet. How do we impose this? So this is best done using Fourier techniques. So suppose I have some arbitrary function, which you can probe on any scale you wish. Then suppose I put it in a box of volume V, L to the power D, and with periodic boundary conditions, etc. Then you will see that I can write the alpha component of phi as a Fourier transform. Okay, the conventions of 1 by square root 2 is a matter of how you define things, but we choose to, in physics typically we define it like this. So it's sum over all these wave vectors. So we also use momenta for wave vectors, because H cross, it's like de Broglie relations. Momentum is equal to H cross k. So H cross is taken to be 1. So we just use, whenever we say wave vector, we also use the word momentum. Okay, so this is sum over all momenta phi alpha of k. So this is the Fourier component, and the Fourier component can be gotten by Fourier transforming the field phi of x. You give me a k, I can Fourier transform it and I can find the Fourier component. On the other hand, if you give me the Fourier components, I will tell you what is the field. So if I want to impose periodic boundary conditions, now, so if I take x1 for example, x1 plus L must give me the same value of phi of x1, right? So when I do that, I will see that these momenta that are allowed, they have to be 2 pi times some integer values. There are d integer values because it's a d dimensional space, and all these mi's, I going from 1 to d, belong to integers. This is how I introduce the the field in Fourier space and imposing periodic boundary conditions. Now, how do I impose this cutoff? Okay, look at this extremely clever trick. So when you say that there is an ultraviolet cutoff, length cutoff, which is LC, you can implement this ultraviolet cutoff by introducing an ultraviolet momentum cutoff. What is momentum cutoff? Lambda is equal to 2 pi by LC, right? So that gives me a wave vector which we are calling momentum. And what I am going to say is that the phi of x that I have here, phi alpha of x, it has only Fourier components with wave vectors less than or equal to, that is a typo, less than or equal to lambda, right. So this should be less than or equal to lambda. So up to lambda we can keep, so it can fluctuate on scales up to wave vector lambda, which means what I'm insisting is that the field phi of x does not have fluctuations with wavelengths smaller than LC. That means that there are no wave vectors greater than lambda, right. So that is what we are imposing. So this is a very clever way of imposing the fact that we do not know the physics below on scales smaller than LC, right. It's a very nice device to do this. So what we have now done is, if we espouse this idea of writing down phi alpha, then we have a field that transforms correctly under symmetry, that is defined on continuum. It can fluctuate, it can, so it can do whatever it wants, and this ultraviolet cutoff is incorporated. So we have now set up the problem, set up the, let's say, the kinematics of the problem, in the sense how to describe the states of my system in terms of this emergent field. So the next thing for us is to find some way of writing the energetics of such a field. So question you want to ask is, how do I, what is the, so in, say for example, the microscopic thing, microscopic model, suppose I give you a spin configuration, I'll tell you what is its energy, and that spin configuration's statistical weight will be proportional to e to the minus beta times that energy. Here my question is, I'm giving you, let's say I give you the configuration of such an emergent field. What is its statistical weight? For that I need to have some notion of what is its energy, in a sense, okay. So this is what the next question is. We need to write down some, we have to have some way of phenomenologically writing down some form of energy associated with such a field, okay. So now you see mathematically what we need is, I will give you a function. So I will give you a phi of x. You have to tell me a number associated with each phi of x. So for every function I give you of this emergent field, you will give me a number which I can call its energy or action or whatever, right. So such a map from a space, from a set of functions to real numbers is called a functional. Okay, I am sure you have encountered this in your previous studies. So the Landau-Ginzburg approach, what it does is, it gives me an energy functional. Okay, so you give me a field, it's called a functional, or we'll also use the word action. You will see later why this word makes sense, right? So you give me a field phi, I am going to postulate that this energy of phi is an integral over the box and energy density associated with phi and so on. So this energy density, if you like, this L, that depends on the value of phi at the point x, the gradient of phi, the second gradient of phi, and all possible gradients of phi. So the postulate is that this functional is an integral of a density. Okay, this is the idea. The density itself depends both on phi, its derivatives, first, second, third, up to whatever you wish, at x. All of these quantities are evaluated at the point x. So in the sense that this is very local, you just need to know the function, the field, the derivative of the field, second derivative, all the derivatives at that point. If you know all of these, I will give you a function which will return me a number for this, and so on. So the Landau function that we wrote down before, it didn't have any information about gradient, so it will be just L of phi, right? So it's an analog where now that I have to include these gradients, etc. So it depends both on phi and its derivatives at x. Second postulate is that this L, this density L, is an analytic function of all its parameters, right? And in writing down this functional, you will introduce some coupling constants. So it's also analytic in those coupling constants. So that is what is there. Okay, and the coupling constants and the terms, etc., will be introduced to reproduce some known phenomenology, like the previous Landau approach. Okay. Now, the most important thing is, when you are constructing these things, this S of phi must be invariant under the ON symmetry. So, for example, if I take if you give me a field configuration and I do a symmetry transformation and I find a new field configuration, this S of phi that I compute from this new symmetry transformed field phi must be same, S of phi must be same as S of transformed phi. So this is the absolutely important requirement, right? In addition, for the first time I am mentioning this in the context of Ginzburg, Landau, etc. If there are any arena symmetries, remember this phi were invariant under ON internal symmetry. Suppose there were also some arena symmetries, for example, you want some translational invariance, rotational invariance, and so on. Then this action function must also be invariant under those symmetries, and we have discussed in a very early lecture how to transform these fields by such fields by arena symmetries. Okay, so this we will not dwell too much on this. We will just apply these ideas very straightforwardly, as you will see. Okay, so those are the general principles for constructing the Landau-Ginzburg theory. Okay, once you have this action functional, then the claim is the following: the statistical weight associated with the field configuration is proportional to exponential negative of the action. This is like e to the minus beta h, it's just negative of the action. Okay, and what is the partition function? So partition function is sum over all configurations, right? So what are the configurations here? They are functions. So what we have is that the partition function is what is called as a functional integral. Functional integral meaning I'm imagining that there is some kind of integration measure, which is what we call d phi, in the space of functions, and I am going to integrate e to the minus s of I. E to the minus s of I is just a number. S of I is a number. E to the minus s of I is also a number. I am integrating this on the space of functions, and this object is called as a functional integral. Okay. So if I get this partition function now, right, and once I have this partition function, I can compute the extensive free energy, the free energy of the full system, by taking f equal to minus log of z. This will give me the free energy, and if I divide by the volume and then do variety of things, I can get the density, etc. And once I have this free energy, we know that we are in the world of thermodynamics, and by looking for non-analyticities of this free energy, we can find points of critical phenomena, etc., and we can analyze this. So this is the idea. So these two slides are very generic. It's not based on an example, it's illustrating principles. So you introduce a field, you say that the energetics associated with the field is a functional, and the functional itself is an integral over a density associated with the field, and the density can depend on the field itself, the gradient of the field, the secondary gradient and whatnot. You can introduce coupling constants here which capture the phenomenology, and this action itself should be invariant under the symmetry, and the partition function is an integral over all possible configurations, but the set of all configurations form a space of functions. So it's an integration on the space of functions, and this is what is the functional integral. And once we have this, we get the free energy. So this is what we have just seen. Okay. So we have now, so that's very general. We would like to now be a little bit more concrete. We want to write down a specific theory here, and then we have to find some connection to experiments, of course. That's always the case. Okay. So this Landau-Ginzburg theory is specified by the density, which depends on phi, gradient phi, and all the other derivatives. Okay. To see an example of such a theory, we need to write down some reasonable density, right? Now, what is reasonable is a difficult question. So the best thing to do is to make use of the experience of our forefathers, if you wish, right? And so if we just look at what Landau and Ginzburg themselves did, and what they proposed was the simplest possible theory where the lowest order gradient is included. So remember, so what they did was they wrote L of phi and gradient phi as, let's look at the familiar term first, AT by 2 phi square plus B by 4 phi to the 4. So this is exactly the Landau density. What they added to this was they added a term which looks like y by 2 gradient phi square. So I have to clarify what this gradient phi whole square means. Okay. So now if I look at this field in d dimensions, this field phi has n components, right? And I can take derivative of any one of this component in any direction. So strictly speaking, this quantity gradient phi, it has d times n objects in it. D being the direction, there are d directions and n components in the ON space. So this gradient phi in component form will look like derivative in the I direction of phi. Okay. Now the notation here of squaring this is that you are contracting the spatial label and contracting the internal label. So when you contract the spatial label, you get a spatial scalar. You get an object which is invariant under rotations and blah blah, right? You will get a spatial scalar. So under any arena symmetry, it will become invariant. And when you do phi alpha, when you sum over alpha, you will get something invariant in the internal, the ON scalar. So this whole thing is a scalar in that even if you do some spatial rotation blah blah, you will get the same value, as well as if you do ON rotations, you will get the same value. So that is what this quantity is. That is the notation here. okay, and that's the expanded version of that notation. Repeated indices are summed, repeated indices are spaced, as well as internal index alpha are summed. So what is this quantity y? The quantity y, it is a term, it's some kind of stiffness that penalizes the change of phi from one cell to the other. So remember, just let me show you the picture of the Ising model quickly. So you see there is phi of x here. So what it wants to do is, if the configuration is such that the phi of x here is very different from the phi of x here, then there is a large gradient, and that gradient is penalized. So what it wants to do, it wants to make sure that the phi of x between neighboring cells are almost equal. That's what it wants to do. So it wants to favor the alignment, if you wish. Okay. So that is the term that we have here. So we have, so this was added by Ginzburg and Landau. So they said that you know, it will penalize the change of phi from one cell to the other, and this is something like a stiffness. So this y is called a stiffness. Okay, these two terms are same as what we had in the Landau theory. So this is the extra term. Now, invariance under ON transformation is by construction ensured, right? So this is ON invariant, and this one is ON invariant, and so arena symmetries such as translation, rotation, etc. are included because I did not make y, a and t and all that stuff functions of space. I have taken them to be constant. If you make y, t or b or something as functions of space, then you will not have translational symmetry, and this is how we are imposing translational symmetry. So we will take the simplest example, we will not go more formally into this. So this you can see clearly that this is how I am imposing translational symmetry. Okay. So this is one very nice, the simplest Landau-Ginzburg action density you can write down, this L that you can write. Okay. So you can ask me a legitimate question now. So what good is this? Can you explain any experiment with this? Okay. So I will flash one slide to show you that this theory was remarkably powerful. It turned out to explain many things in superconductivity. It showed that you know, you can have different types of superconductors and so on. We will of course not have time to discuss all that. I will just show you very briefly on this single slide that it shows this effect of current. Okay. All right. So now recall that in the previous lecture I showed you the connection between O2 and U1. So it turns out that it is much easier to discuss this in the U1 language. It's the same as O2, a little bit different mathematically, but it's the same physics. So Landau and Ginzburg said that the emergent field of a superconductor or a superfluid is a complex field. So this psi of x is a complex number at every point x. And they wrote down an action which is which action density, if you like, L of psi and gradient psi. So that is y by 2. So this is the stiffness term. I am contracting the spatial index here. So it's a spatial scalar. And you see this is a star complex conjugate with psi. So you see if I do some phase rotation on psi, if I make psi equal to e to the I theta psi, this will go to e to the minus I theta psi, and therefore that e to the minus I theta and e to the I theta will cancel each other, and you will end up getting something invariant under the U1 rotation. And these things by construction, they will not be affected by the phase of psi. So any U1 action on psi will leave this terms invariant. So this is the theory. And if we just ignore this gradient term, if I simply ignore the gradient term and work with this, I will actually find that there is a phase transition when little t becomes less than 0, and I will get an order parameter in this context of U1 that's called as the delta, the superconducting order parameter delta, which will go as square root of mod t, right? This is beta equal to half exponent result. So this is very clearly understood. Now suppose I go to t less than 0. what is the phenomenology I know? I know that if I pass a current through this, then I am going to destroy the superconducting state. That is what I know. Can I see this show up from this theory? Right? So let me show you that. Now imagine that I have a state, right, where psi of x, this emergent field, the magnitude is constant in space. So the psi, mod psi is constant in space. So I am just writing it as mod psi. Its phase on the other hand, theta, is varying in space, right. Now just recall from your quantum mechanics, if I have a wave function whose magnitude is fixed in space, but the phase is changing, then you will see that wave function corresponds to a state of the particle carrying a current, right. So how do we see that? So for example, the current itself of any wave function can be written as current density, if you like, is 1 by 2i times psi star gradient psi minus gradient psi star psi. So what you can do is, suppose you choose theta of x, this phase, as varying linearly in space in this fashion, a q dot x. That means if you are going in position space, if you are parallel to the q, the phase is changing. If you are perpendicular to q, the phase is not changing. So it's like, you know, I have planes of constant phase. So basically my phase is varying linearly along the q hat direction, right, and a is some constant. So what you will see, if I take this, write down the wave function like this and note that the mod psi is not varying in space, then I will find that the current is equal to mod psi square, which we have fixed, a times q. So what is clear is that if I input such a state, then that state corresponds to a state carrying a current. Okay. So this is how I am constructing a state which is carrying a current. Okay. Now what I am going to do is, I know now that the psi depends on position like this. So I can now see that if I treat this mod psi as an unknown quantity which is constant in space but unknown, and I impose theta of x goes like this, then this functional can be computed exactly, this density L of mod psi, because it now depends only on mod psi. So you will see that this gradient square term will give me mod q square. So that should be a vector q, but you will see that it's just mod q square. And then y times a times this, right? So this stiffness times a is this this constant, right? Right. So that's the result. Okay. All right. Now what I do is I try to see at what value of mod psi is this going to be minimized. But now you realize that if I keep increasing q, which is that I am increasing the current, then a critical q will show up where this quantity becomes positive. But we know that if the quantity multiplying mod psi square becomes positive, then the minimum value at which, L of psi is minimized will be 0. That means this mod psi will die and I will not have any order parameter. My order parameter will vanish. Okay. So what this is showing is that there is a critical current which is given by this expression, right? And this theory, after putting in this gradient, this is the Ginzburg-Landau theory, shows that the superconductor has to have a critical current, right? And that's exactly the experiment. So this is what is shown here, is this delta as a function of t, little t. So this is t by tc. So you can see that delta is going up like this, right? And this is a plot of applied field, current and temperature. So when I go below Tc, I am in the superconducting state. So let's say I am here and I increase the current. When I show up here, I hit this phase boundary of going from the superconducting state to the non-superconducting state, and that current will be given by this. So you can see that we are with this very nicely argued phenomenology. Landau and Ginzburg were able to show that to capture the physics of superconductivity in a simple model like this. Okay, so the message is that our goal was to find out why Landau exponents are not dependent on space dimension and variety of things like that. So we went and we tried to include fluctuations, but as an outcome we were also able to connect to some experimental phenomenology of superconductors, which is very nice. Okay, all right. So let me summarize this lecture for you. So Landau-Ginzburg theory produces super universal critical properties, which is, well, not so nice because it doesn't agree with experiments. It does not agree with analytical theory or numerical results. Okay, so to address shortcomings of Landau theory, we noted that the Landau critical exponents are same as mean field exponents, and we know fluctuations are missing in mean field theory. So we decided to put in fluctuations. Then we realized that if we want to put in phenomenologically these fluctuating fields, then we have to make our emergent field a function of position. But then when we do that, we have to explicitly acknowledge that we are coarse graining and there is an ultraviolet cutoff scale LC. So we found a way to deal with that. And then we have to write down an energetics. You have to write down a formulation where whenever you give me a configuration of this emergent field, I have to give you an energy associated with this, so that we can attribute some statistical weight associated with the field. And then when we want to compute the partition function is sum over all these configurations, which is an integral over the space of functions. So that's called a functional integral. And this energy functional, this itself is postulated to be some integral of density, etc. Right? And we have to design this S of phi so that it is invariant under the symmetry transformations, etc. and so on. And as a small reward for our work, we were able to take the Landau-Ginzburg theory and immediately connect up with some phenomenology of superfluids and superconductors, which is very nice. But if you pause for a moment, you will realize that I did not discuss what do we actually mean by the functional integral. How do I actually do the calculation? So if someone asks you what is integral dx of x, you know it's x square by 2. But suppose I give you some functional, how do we calculate it? So this is something we didn't discuss in this lecture, and we should definitely discuss it if you want to take this to a calculation and find this, and that's what we'll do in the next lecture. And we will start exploring the physics of the Landau-Ginzburg theory in the upcoming lectures after having introduced the functional integral in the next lecture. So I'm sure you will want to know about functional integrals, so please join me for the next lecture. Thank you.